Hey everyone, and welcome to the Service Mesh with Istio course. I'm Sevi Karakose, and I'll be your instructor for this course. I've worked as a software developer and then a team leader for many years. I've also done technical trainings, worked with development and infrastructure teams on DevOps transformation, and also designed team activities for organizations to be more adaptive to change. Now, as a cloud native engineer, I work with development teams on their legacy applications for microservices transformation and cloud modernization. In this course, we will learn Istio through some lectures and many lab activities. We'll start from the basics of Istio and learn step by step with examples and hands-on labs. By the end of this course, you will have an extensive understanding on how to configure and manage your service mesh with Istio. Let's look at the objectives of the course. First, we start with an introduction to Istio. We learn about monoliths and microservices and why we need service mesh through example-driven lectures. We then get introduced to Istio. We learn how to install Istio and configure it. And we finally look at how to visualize our application and services with KLE. We then drill into Istio concepts such as gateways, virtual services, destination rules, subsets, timeouts, retries, circuit breaking, fault injection, request routing, A/B testing, etc. Next, we look at the security aspects such as certification management, authentication, and authorization. And finally, we look at observability such as viewing and collecting metrics with Prometheus and Grafana. We then look at KLE in a bit more detail, and finally, distributed tracing. I am super excited to take you through this journey, so let us begin. In this section, we will talk about some of the prerequisites you need for fully grasping the concepts and implementing them in this course. As a prerequisite, you must have basic Kubernetes knowledge, such as how to deploy a basic Kubernetes cluster, basics of pods, replica sets, deployments, and services in Kubernetes. If you are new to Kubernetes, I would recommend starting with our Kubernetes for Beginners course. We will, however, recap some concepts that are important to understand service meshes and Istio, such as Kubernetes services, sidecars, and Envoy proxy. If you are already familiar with these, feel free to skip this section and go straight into the introduction of Istio. On a side note, you don't necessarily need to set up a Kubernetes cluster while going through this course, as you will be using the lab environment that comes with this course. However, we have some demos that will help you set up your own environment if you would like to try a local setup. In this section, you will be introduced to microservices and how they evolved, how service meshes came into the picture. And then we will talk about Istio, one of the most popular service meshes right now. We will talk about how to get started with Istio by installing istio utility first, and then installing Istio on your cluster. We will see how to deploy our example application in our cluster, generate some traffic, and visualize it with the Kiali dashboard. Kiali helps in visualizing traffic in a nice user interface. So this will be helpful for us to understand how our mesh works. At this phase of the course, we will look at a high-level overview of Kiali and learn how to install it and view the dashboard. But later on, towards the end of the course, we will dig in deeper. If you're ready, let us begin. Before diving into Service Mesh and Istio, I'd like us to have a look at the evolutionary changes in software design in the last 2 decades. The 2000s started with a breakthrough proposition that would completely change our view of software development. At the time, software development had become very process-oriented and slow. For some industries, like defense and aviation, for example, it took almost 20 years for a project to finish. There was a huge time gap between the software need arising and the software being delivered. Businesses changed before even the software projects got delivered. Many projects had been laid off before even it was finished, and so much money was wasted. Business owners and software professionals both were frustrated. So in 2001, 17 independent-minded software practitioners got together and published the Agile Manifesto. They told the world that the way people created software had major flaws and needed to change. From the experience they had, they decided to value individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, responding to change over following a plan. That is, while there is value in the items on the right, we value the items on the left more. Based on Agile practice, not only do we collaborate with our customers more, but also we evolve our business models and software based on true experimentation. When you are working on one large app, and if something breaks, it breaks entirely. However, if you're changing small portions of your app, things would be more under control. The piece that you're experimenting with might be affected, but the risk will be less than before. So we started designing our applications to be smaller and smaller so that we can isolate risks during experimentation. At the same time, deploy faster and more frequently. So the giant systems we have been designing have been becoming one big problem, standing in the way of innovation and agility. We had to take a look at our traditional software architectures and redesign them. The term monolithic is used when all the functionality in an app needs to be deployed at the same time and there's a unified approach to all the separate functionalities within the monolithic boundaries. All of this functionality almost always shares the same code base and it has no clear boundaries between them. These pieces are tightly coupled. All the code could even be working as a single process. There's usually a single database for persistency in this model, which becomes a huge bottleneck at one point. Let's see how a monolith works in a real-life application. Here is our book info application. We will use this as our example application throughout this course. It consists of 4 different modules, namely details, reviews, ratings, and product page. It is a modular application, but still a monolith. All the services depend on a specific version of the other one. You need to deploy the whole package and possibly send some scripts to the database. The product page shows the book's information, reviews, and ratings. All the data of this application comes from different modules, but they are not separately designed and cannot be scaled. Let's try to understand the dependencies of the modules and the problems of the monolithic book info. The customer lands on the product page. Product page gets this information from reviews and details modules. Review service gathers the number of ratings from rating service. They are all written in the same language, Java. Apart from these modules, the application also takes care of networking, authentication, authorization rules, and how data is transferred between modules, logging, monitoring, tracing, etc. Every once in a while, the ratings module, because of the amount of the data it holds, have problems, and this affects the whole system. It is not possible to just scale ratings or leave it out of the system without touching the code and redeploying it. Now, a new campaign module is going to be developed. But this time, a new team is formed for this, and they want to use a different language. Since everything is unified and all the important functionality like authorization lies within the monolith, they have a hard time designing the architecture. And also our product owners want to try a new version of reviews with red stars for Christmas. They want to test this functionality on a segment of users, and if they like it, we can use it for the whole system. This is not possible without deploying the entire application in 2 different versions. This is a very simple app with very little functionality, and you can see the problems we are having to tackle already. Now think of huge applications that have been around for decades and more. There may be hundreds or more developers working on these systems, and starting with some loose rules on architecture, these systems might become a big ball of mud. Big ball of mud is a famous idiom for these types of software systems. Without noticing, your monolith application can go out of hand and become one of those. Let's have a look at how this book info monolithic application could magically and miraculously turn into microservices. Well, to be honest, it is not an easy task to refactor monoliths, and it's not an overnight transformation. It is a cultural, technical, and organizational effort which paves the way to being cloud native. With the new microservices architecture, each module is now its own independent and separate application. Our product page has been transformed into a Python app. It still functions as our landing page. The book details module has been refactored into a Ruby application. The reviews module has been transformed into a Java app. The ratings module has now been redesigned and implemented in Node.js. Moreover, the reviews app now has multiple versions: version 1, version 2, and version 3 to test different ideas. Version 1 is a no-star version, version 2 is a black star, and version 3 is a red star version. As before, users land on the product page, which contains the details and review services to show information regarding various products. So now that we have seen how the monolithic book info application has been transformed into microservices, let's talk about the improvements and wins. The ratings module will not be a problem anymore. Now that it is fully independent, we can scale it up or down depending on the load from our customers. We can now deploy every piece of book info without interfering with others. It will make our releases smaller, faster, and less risky. With microservices architecture, each service can be written with different languages. So here in our application, we have now 4 different languages and each team has autonomy. Our services are now isolated from failure of other services because of the loose coupling. And the end-to-end application will have more resilience since its different parts can be monitored, changed, or rolled back easily. Instead of having one big application, we now have 6 smaller applications. So hopefully, you won't have to deal with a big ball of mud anymore. In an ideal scenario, a microservice should have a single responsibility. Earlier, when we discussed the monolithic book application, we said that, apart from the 4 different modules, the application also takes care of networking, authentication, authorization rules, and how data is transferred between modules as well as logging, monitoring, etc. But what happened to these when we moved to the microservices model? Well, they are not there. Our microservices currently do not implement any of these. We could move these into each of our R services. So let's add all these functionalities to our microservices. By now, you probably have an idea on where this is going. Every microservice boundary has the same functionality coded again and again into them. Every team has to solve the same issues over and over again, and probably they'll solve them differently. Look at the code application here, and how do you go tell these teams to change a certificate or a monitoring agent version? Any developer developing any of these applications will need to be aware of all of these extra components apart from the core business logic that microservice is meant to serve. These issues we have to deal with in every microservice are called cross-cutting concerns. When coded into the microservice, they disrupt the main reason we designed the microservices: to be able to have smaller, more independent pieces. This is known as the problem of fat microservices. Microservices are not a piece of cake. They have their own challenges and they tend to get really complicated. As we just saw in the monolithic version of our application, all aspects, such as networking and security, were directly coded into the application. But now, all those gray areas fabricated into our monolithic application are exposed, and we have to find a way to cover them. How will the product page know which version of reviews to go to? So, how will one service know how to find the other one? What are the traffic rules? What are the timeouts? In a very short time, you'll have too many tiny bits of services spread out, and these questions will get much harder to answer. It was much easier to handle the security in our monolith because it provided the proper scheme for us. In our microservices, securing service-to-service communication and end-user-to-service communication can become a problem itself. Now that you have loosely coupled tiny pieces and many abstraction layers, it gets harder to pinpoint a problem in your application. For that, you will need an observability strategy. Just for a small application, we used 4 different languages. With all those different technologies of microservices, it gets very demanding to do traditional operations. Actually, operations might become a bottleneck for organizations who take on microservices. There's a new approach for that called DevOps, where the development teams work closely with operations and together they take the responsibility of their microservices for deploying, monitoring, and fixing. In the upcoming lesson, we will look at how service meshes can help solve these challenges with microservices. So, what is a service mesh? This is where we were in the previous video. Instead of embedding all the different requirements into each microservice, we replace them with a single proxy in the form of a sidecar container. The proxies communicate with each other through what is known as a data plane. And they communicate to a server-side component called control plane. Control plane manages all the traffic into and out of your services via proxies. So, all the networking logic is abstracted from your business code. And this approach is known as a service mesh. A service mesh is a dedicated and configurable infrastructure layer that handles the communication between services without having to change the code in a microservice architecture. With a service mesh, you can dynamically configure how services talk to each other. When services talk to one another, you'll have mutual TLS, so your workloads can be secure. You can see things better. For example, how the application is doing end-to-end, where it is having issues and bottlenecks. And service discovery, which covers 3 main topics. In a dynamic cluster, we will need to know at which IP and port services are exposed so they can find each other. Health check helps you dynamically keep services that are up in the mesh, while services that are down are left out. Load balancing routes the traffic to healthy instances. and cuts it off from the ones who have been failing. We will look into each of these in more detail throughout the rest of this course. I'll see you in the next one. Now we'll have a look at Istio, how it works, its architecture, and its core components. Istio is a free and open source service mesh that provides an efficient way to secure, connect, and monitor services. Istio works with Kubernetes and traditional workloads, thereby bringing universal traffic management, telemetry, and security to complex deployments. Istio is supported and implemented by leading cloud providers and consultants. Earlier, we talked about the proxy service that takes care of all the tasks that should be outsourced from the microservice. These proxies and the communication between them form the data plane. Istio implements these proxies using an open-source high-performance proxy known as Envoy. The proxies talk to a server-side component known as the control plane. Let's look at these in a bit more detail. Originally, the control plane consisted of three components, named Citadel, Pilot, and Galley. Citadel managed certificate generation. Pilot helped with service discovery, and Galley helped in validating configuration files. The three components were later combined into a single daemon called istio1. Each service or pod has a separate component in it, along with the Envoy proxy called the Istio agent. The Istio agent is responsible for passing configuration secrets to the Envoy proxies. So, that's a high-level overview of Istio. Next, we will get started with Istio by installing it, and later we will dig deeper into Istio's features and functionalities. Now, it's time to install Istio on our cluster. There are three different approaches to install Istio. We could install it using the command line utility istio1. We could use an Istio operator to install it, or we could use a Helm package for the same installation. For this training, we will use istio1 for installing Istio on our cluster. To install Istio using istio1, run the istio1 install command and specify a profile. For this installation, we will use a demo profile. There are also different profiles for production and performance testing. We will not use them in our training, but it's important to know that different environments need different profiles. When this command is run, Istio is deployed in the cluster in the form of a deployment named istio1 in a new namespace known as the Istio system namespace. Istio1, as we discussed earlier, has different components inside it, such as Citadel, Pilot, and Galley. Along with these, it also deploys two other services known as the Istio Egress Gateway and Istio Ingress Gateway, and a bunch of Kubernetes service objects to expose these services within the cluster. We will talk more about these gateways when we talk about gateways in a later section. Once installed, run the istio verify-install command to verify the installation. You'll see a huge list of items here. As we talked about earlier, Istio extends Kubernetes, so you can see CRDs here. Let's now see this in action in the upcoming demo. So, for this demo, you'll need Minikube installed on your machine. First, let's create a cluster in Minikube. If you use start Minikube command, Minikube will use the default driver. As you can see, I also have Docker running in my system, and I'm using Docker as my default driver. If Minikube finds that you're running Docker on your local system, it just lends itself as a container in Docker. You might as well run into this issue that says, due to the networking limitations of driver Docker Darwin, Ingress add-on is not supported. So, this bug is all about the Ingress add-on not being supported on Docker driver on macOS due to the limitation on Docker Bridge for Mac. By the time this training is released, the bug might be resolved and you might not hit the issue. But if you did, here's a way to make it work. Let's delete this cluster and use this command. Now, you can use Minikube with a VM-based driver, as it will not work on Docker. Instead, it will work in a VM. Let's try enabling Ingress. Yes, we see that it's enabled. Now, with this command, we will install istio1, which we will use in this training a lot. Be careful, this command will download the latest Istio release to the current directory, so make sure you download it somewhere safe and relatable. At the time of this recording, the latest release of Istio is 1.10.3, so this might be different in your case. Now, move to the Istio package directory. This directory is also named with the Istio version we downloaded. Let's see what we got with the Istio package. We have the license and README files. There are lots of samples in the samples folder, and istio1 client binary is in /bin. In the samples folder, we have our sample application that will be used throughout the course. And also there are other interesting examples. You can go search for more information in the Istio docs. Let's see what's in the tools folder. Nothing much. Now with this command in Linux and macOS, we add the istio1 client to our path. Let's check if istio1 is installed. Yes, it is, and it is running in 1.10.3. Now, using the istio1, let's check if our cluster has Istio installed. Well, that's because it does not. As you can see, it is telling telling us there is no Istio control planes. Let's install Istio on our cluster now. So, in this demo, we'll be installing Istio on our cluster using istio1. For this, let's use istio1 install command. As we have talked earlier, for demo purposes, we'll use demo profile. Let's run this command now. Once installed, let's use the verify install command to check if everything is installed without any problems. As you can see, now in our cluster there are a bunch of new resources that Istio has added. Some of these are cluster roles, cluster role bindings, custom resource definitions, and 3 Istio deployments with 13 custom definitions. Our Istio cluster is installed and verified successfully. Let's move on to the next section. Now to try Istio, let's deploy our application. In the samples folder we downloaded, you will find the sample bookinfo application. To deploy it, please use this command. If you have Istio samples somewhere else on your computer, you can also change this directory. In the output that follows, you will see a number of deployments and services created. Let's check the status of the pods deployed. We see that we have a pod for the product page microservice, the details microservice, the rating service, and 3 different versions of the review service. We see that everything is deployed in the default namespace. And now that we have Istio installed, we expected each pod to have the additional proxy container that we talked about. However, that is not to be seen. We can see that each pod only has a single container as shown in the red column here. So why is that? We can use the istio1 analyze command to see why that may be the case. It seems that we have a problem here. The analysis tells us that Istio injection is not enabled. What does it mean by namespace is not enabled for Istio injection? You might be having multiple namespaces on your Kubernetes cluster. Kubesystem being the namespace where all the core applications run, and the default being the default namespace where applications are deployed when no namespace is specifically given, as it is in our case. There may be other applications running in other namespaces, such as HR or payroll, etc. You must explicitly enable Istio sidecar injection at a namespace level if you would like Istio to inject proxy services as sidecars to the applications deployed in a namespace. For this, as given in the output of the command, you must run the kubectl label command to specify the namespace where you want to enable sidecar injection by setting the value of the label Istio injection to enable. Similarly, if you'd like to explicitly disable Istio injection, Then you must set this label to disabled using the same command. We will now delete what we deployed so we can set the label and deploy it again. Let's enable Istio sidecar injection in the default namespace. In the default namespace. Once this command is run, every new app in the default namespace will get a sidecar automatically. Let's deploy our app again. Let's check the status of our mesh now. Let's check if we have Envoy sidecar proxies. Yes, they're here and running. Istio has now injected sidecar proxies into each pod. You will explore more about these in the upcoming labs. Well, that's it for now, and I'll see you in the demo. So in this demo, we'll deploy the Bookinfo application on our cluster, enable sidecar injection to run our Envoy sidecars properly, and prepare our mesh for our first interaction with it. For this, we're going to use the Bookinfo app under the samples folder we downloaded with Istio. So, it's here in the platform directory. Let's apply it with kubectl. As you can see, each service has service account, and deployment objects described in this file. You can even see the 3 different versions of reviews deployed already. Let's check the status of our pods. So, they are all ready and running, which is nice. This means our application must be running properly. But do we have a service mesh in place? Here, as you can see, there's only one container for each of our pods, which is not a very good sign. Why could this be happening? Let's use istio1 analyze command here to check if there's anything wrong. Oops, there's an info message about the default namespace here. It says default namespace is not enabled for Istio injection. This is because we need to explicitly mark a namespace for injecting Istio sidecars into the pods in that namespace. Let's use this suggested approach here to label our namespace. Yep, it is marked. Now, to get this working, we need our pods to be recreated. A fast way to do that is to delete all our deployments and create them with our initial YAML file. Here it has only created the missing ones, and the rest is not changed. Now, let's check our pods once again. Yes, they have sidecars injected to each one of them. Here, an older deployment still has some pods in terminating state, but it's just a matter of time that it disappears. And yes, it did. Okay, so let's try istio analyze command once again. It is telling us the command just analyzed default namespace and found no issues regarding istio objects. Congratulations! We now can start building our service mesh.